As philosophers, we always find ourselves grappling with the systems of logic that underpin our arguments, right?
Yeah, absolutely.
And I don't know about you, but there are times when I sort of feel a little shaky about those foundations. Like when you come across those paradoxes,
Oh, yeah.
the ones that seem to just completely unravel any hope of consistent thought.
Those are the best.
Well, today we're going to explore a system that came about directly because of those kinds of intellectual head scratchers. It's called type theory. And it's not just some historical footnote. It's actually still incredibly relevant today. It's shaping how we think about logic, math, even computer science in some really surprising ways.
You got it. Type theory, it's really like a philosopher's toolkit. It helps us build logical systems that are, well, more robust, let's say. And the way it does that is by focusing on how we classify the things we reason about. The goal is to sidestep those self-contradictory statements that can just make our arguments implode.
That makes sense. And to guide us through this complex world of type theory, we're turning to the Stanford Encyclopedia of Philosophy. Their entry on type theory is, well, it's pretty comprehensive. So think of this deep dive as your curated tour through a system that's had a huge impact on logic, math, and yes, even programming languages. Our mission today is to understand why type theory came about in the first place. Those pesky paradoxes are a big part of the story. And then to trace its fascinating connections to things like computer science and category theory.
The story starts with those very problems that really threw a wrench into the works for logicians and mathematicians at the beginning of the 20th century, the paradoxes.
Oh yeah, those paradoxes. Okay, so one of the most important ones was Russell's paradox. It's all tied to Cantor's theorem. And Cantor's theorem, basically, it says something fundamental about sets. It says that the set of all possible subsets of a set, what we call the power set, well, it's always bigger than the original set. Cantor actually proved this using a really clever method called diagonalization.
What's so neat about Cantor's diagonalization is how simple it is. You just imagine that you have a set, any set will do, and you're trying to match up every element in that set with one of its subsets. You want a one-to-one pairing. What Cantor showed was that you can always cook up a subset that gets left out, that doesn't have a match. And this leftover subset, it's made up of all the elements in the original set that aren't in the subset they're supposed to be paired with. It's subtle, but it's really powerful reasoning.
It is. And this is where Russell comes in. He took this idea and applied it to something even more basic, the class of all classes. So he asked, can you have a collection of absolutely everything that can be a class and have that be a class itself? And it led him to this specific kind of class, the class of all classes that don't belong to themselves. We can call this, say, W, mid-W, and WO. It's kind of like that classic paradox about a barber who shaves all men who don't shave themselves. Can he shave himself? It's a self-referential loop that just creates this mind-bending contradiction.
And the paradox just pops up right away when you ask, does R belong to itself? If it does belong to itself, R and R, then by its very definition, by the rules of the game, it can't belong to itself.
Yeah.
But on the flip side, if it doesn't belong to itself, then it actually fits the condition for being a member of.
Yeah.
So it should belong to itself. It's a logical knot you can't untie. A real head scratcher.
It really is. It's interesting that even Cantor himself had an inkling that this set of all sets thing was tricky, even dangerous. He was sort of foreshadowing what Russell later made so clear. And Russell, when he realized what he'd stumbled onto, he wrote to Frege about it.
Ah, Frege. His work at the time was seen as, well, it was considered to be rock-solid foundation for arithmetic.
It was. So how did Russell express this paradox in Frege's seemingly unshakable system?
Right. So Frege's system didn't directly allow for something like R mid W because he had this fundamental separation between what he called predicates, concepts and objects. A first-order predicate in his system could apply to an object, but it couldn't be the subject of another first-order predicate. It was his way of trying to stop certain kinds of self-reference right from the get-go.
Clever. So how did Russell manage to slip this paradox past Frege's defenses?
Okay, so Russell used this idea of the extension of a predicate. Frege had a symbol for this, for epsilon p. Now, the extension of a predicate, it's basically the collection, the set of all objects that fit that predicate that make it true.
I see.
Crucially, in Frege's system, this extension was treated as an object itself. And Frege had this really important axiom, axiom V, which said that two predicates have the same extension if and only if they're materially equivalent.
Meaning
They're true for the exact same objects.
got it.
So Russell, with this clever trick up his sleeve, reformulated his paradox using extensions. He defined a predicate, which is true if the extension of some predicate, let's call it P, where P happens to be false. And then using axiom V, he managed to derive this contradiction.
Equivocally pointed out here, especially for a philosophical mind like yours, that the way Russell defined this involves what we call impredicative existential quantification over predicates.
Impredicative.
Yeah, it means that we're defining R by talking about all predicates, and that includes R itself. It's this kind of circularity that tends to be at the heart of these logical paradoxes.
I'm starting to see the pattern here. So even with Frege trying to keep predicates and objects separate, Russell found a way to sneak in self-reference through this concept of extensions and impredicative quantification. It's remarkable that Frege was already working with what we now understand as an extensional hierarchy. Objects, predicates that apply to those objects, then predicates that apply to those predicates, and so on. It's as if he had the ingredients for a typed system, he just hadn't quite put it all together.
You're right. And Russell saw that you absolutely needed this kind of hierarchy to avoid the paradoxes.
He did. And that underlying need for structure that was kind of lurking in Frege's work, well, it became the foundation for something called simple type theory. It was developed by people like Tristek and Ramsey. They thought that if you kept those levels, objects, properties of objects, and so on, totally distinct, well, it looked like you could block the kind of self-application that led to Russell's paradox.
It seemed promising, for sure.
So how did they formalize this? How did they make it rigorous?
Well, in their massive work, Principia Mathematica, Russell and Whitehead, they laid out a specific type structure. They started with these basic categories. A type for individuals, the basic things they called this. Then a type for propositions, statements that can be true or false, they called that. And then they said, if you already have some types, say A1, A2, all the way to AN, well, you can build a new type, A1, A2, Aelbutz, and A. This represents relationships and area relations that hold between things of those types.
Okay, so let me try to wrap my head around this. If I want to talk about a relationship between, say, two individuals.
That would have type.
Well, exactly. What about logical connectives like and or?
Those take two propositions, right?
Yeah.
And they spit out a new proposition. So their type would be...
Oh, what about quantifiers? Like for all...
That applies to individuals. So
Right.
I have a type, right? It takes a property of individuals, which gives you a proposition when you apply it to an individual, and it returns a proposition.
Okay, I think I'm starting to see the logic here. But what's the real key here? How does this structure actually prevent those paradoxes?
The crucial thing is this type structure sets strict rules on how you can form statements that make sense. If you've got a relation of a certain type, like A1, A2, L-dots, you're only allowed to apply it to things, arguments, that match those types. That's it. This brilliantly stops self-application in its tracks.
So, for instance, if you have a predicate, let's call it P, that applies to individuals, its type would be I, right?
Right. It takes something of type I, an individual, and gives you a proposition.
So PP would just be nonsense in this system.
Exactly. P expects an argument of type I, an individual, but it itself is not an individual. It's a predicate. It has type I.
It's like trying to fit a square peg in a round hole. The rules of the type system just won't let you do it.
That's a great analogy. The grammar of the system prevents that kind of self-referential mess from even being formed.
Brilliant. So simple type theory elegantly sidesteps those direct self-referential paradoxes like Russell's. But as I understand it, it's not quite what you call predicative.
Right. It means that it still allows for definitions that, well, they sort of sneakily quantify over a collection that includes the very thing you're defining. It's a kind of circularity that Russell later tried to eliminate with something called the ramified hierarchy.
Okay, I'm curious about that. But first, can you give me an example of this impredicativity within simple type theory, just to make it concrete?
Sure. Let's say we define a relation, call it QXY, between two individuals.
So it has type, I.
You got it. And let's say QXY means for all predicates P is true, then P is true. Now imagine we have two individuals, A and B holds true.
Okay.
Now let's define a specific predicate as just meaning QXA. Since Q is definitely true, because any predicate will imply itself, right? Then our new predicate also holds true. And because we assumed QB, it follows that P must be true too. That means QB is true.
Whoa. So we've shown that QB implies, using a definition of Pat, that itself relies on the very thing we're trying to define in the first place.
You got it. That circularity, that's the hallmark of an impredicative principle.
Fascinating. So simple type theory avoids those in-your-face paradoxes, but it still has a bit of a roundabout way of defining things in some cases. You mentioned earlier that Gödel and Tarski came up with other formulations of type theory that focused just on classes or sets. How did those work?
Those formulations aim to simplify things by just focusing on a clear hierarchy of sets. They started with type 0, the individuals, then type 1, which contains sets of those individuals. Type 2 had sets of individuals, and so on. It's a simple idea, really. Relations, the things that connect multiple objects, well, they could be represented as sets of ordered pairs, and you could even define ordered pairs themselves as sets of sets. Wiener suggested that.
So it's all about membership. You're saying a statement like object B of type n has property of type n plus 1 just means B is a member of the set.
Exactly. It's really elegant. You start with individuals, then you build the set of all their subsets, which is your next type,
Yeah.
and you just keep going. You can even take this process into the transfinite realm, like Scott explored later on in relation to set theory.
It sounds clean, conceptually. But in these set-based formulations, did they have functions? Were functions a fundamental part of the system?
No, they weren't taken as primitive. Instead, functions were represented as special kinds of functional relations.
Ah, I see.
Then Church came along in 1940 and offered a really different and more elegant approach. He put functions front and center using something called lambda calculus. This was a big development, not just for logic, but because it had these deep connections to computation, category theory, and it really influenced later type theories like Martin-Luff type theory.
So tell me about Church's system. What are the basic pieces?
Okay, so in Church's system, you define types using a few simple rules. You start with two basic types, I for individuals and O for propositions, or truth values.
Simple enough.
And then you have a rule to make new types. It says if you've got two types, A and B, then A right oral B is also a type. This represents the type of all functions that take an input of type A and spit out an output of type B. And you can keep applying this rule over and over to build more and more complex types.
Oh, I see. So this gives you a way to categorize things in a much richer way, right?
Absolutely. Now, you can express things like predicates. A predicate that applies to individuals is just a function from individuals to propositions. So I write arrow.
Right. And a predicate that applies to those predicates would be...
I write arrow O. Right oral.
And what about functions that just map individuals to other individuals?
I write oral, of course.
Easy peasy. And then you've got even more abstract things like, what were they called? Functionals?
You got it. Those are functions that operate on other functions, like I write a arrow. And remember how we talked about n-array relations in the Principia system? Those have a natural counterpart here as a function type. A1 right arrow, A2 right arrow, and right arrow.
I do. That's pretty neat how it all fits together. So what's the language like for expressing these types?
It's based on lambda calculus. It's really a powerful, concise notation for defining functions without having to give them names. The most basic form of a lambda term, let's call it m, can be just a variable, like x. Or it can be the application of one term to another, like mn. Or you can have an abstraction. It looks like this. Lambda xm. This basically represents a function that takes an input called x and returns the value of the expression m, where m might have x.
So you're saying lambda xm is like a blueprint for a function and x is like a placeholder for the input.
Exactly. And the key operation in lambda calculus is called beta reduction. It says that lambda xn simplifies to m with every instance of x replaced by n.
Oh, so you're just plugging in the input into the function's definition.
That's it. Beta reduction captures the heart of function application. It's a really elegant way to represent how computation works at its core.
It is. Now, I remember you mentioned that Haskell-Curry had this idea that types are like predicates that apply to these lambda terms.
Right. So you'd write something like MA to mean that the lambda term M is of type A, meaning it follows the rules of that type.
Makes sense. And this way of thinking leads to some rules about how types work with function application and abstraction, right?
Yeah. So let's say you have a function, call it N, that has the type A right ROB. That means it takes something of type A and gives you back something of type B. If you apply this function to an argument, M, that has type A, then the result, NM, will have type B. It's like the type flows through the application. And with abstraction, if you have some term of type B that might have a free variable x in it, and x has type A, then lambda xm would represent a function with type A right ROB.
I'm following. So how do you incorporate logic into this lambda calculus world?
You bring in special constants for the logical connectives, like not, which would have type or right arrow O because it flips a truth value. Then you have imply, which is or right arrow O because it takes two propositions and gives you another one. And is the same, or right arrow O. And then there are quantifiers, like for all, which would have a type like arioro retiro, because it takes a predicate over type A and gives you a proposition.
Okay, that makes sense. But what about something like equality? Can you even express equality within this framework?
You sure can. You use Leibniz's definition of equality, which says that two things are equal if and only if they satisfy all the same predicates. You can write this in lambda calculus as q lambda x, lambda y, for all, lambda p imply.
Mm.
But here's a little wrinkle for you to ponder. Even this definition of equality turns out to be impredicative, because it's quantifying over all predicates, which could include q itself.
It's like that circularity keeps sneaking back in. So even lambda calculus, for all its elegance, doesn't totally escape impredicative definitions. But it does seem to offer a clearer way to see why Russell's paradox doesn't pop up.
That's right. If you try to define Russell's paradoxical predicate as a lambda term, like r lambda xx, and then try to apply it to itself, you get this never-ending chain of beta reductions, r, right, r, and on and on.
It's like it gets stuck in a loop, forever trying to define itself. It's not just a contradiction, it's an infinite regress.
That's it. And a really important result for simple type theory is something called the normalization theorem. It says that any well-typed lambda term will eventually reduce to something called a normal form, an expression that can't be reduced any further. And even better, any way you try to apply beta reductions, it'll always stop eventually. This basically prevents the kind of never-ending behavior you see with the untyped Russell's paradox.
So the rules of the type system ensure that those troublesome self-applications and infinite reduction loops just can't happen.
You got it. The system's got built-in safeguards.
Very cool. Now we've got to talk about this ramified hierarchy. As I understand it, Russell didn't invent this to fix formal paradoxes within a system. It was more about a philosophical worry about circularity. Like with the liar's paradox, this statement is false. Or that one about the least integer not definable in less than 100 words. So what was his thinking behind this ramified hierarchy of types? What was he trying to achieve?
Russell was really bothered by definitions that seemed to refer to a whole category that already included the thing being defined. It felt circular to him.
Can you give an example?
Sure. He talked about predicative properties, like saying Napoleon was Corsican. That doesn't involve talking about all possible properties, right? It's just a simple statement.
Right.
But then you've got impredicative properties, like Napoleon had all the qualities of a great general.
Which seems to refer to the whole collection of those qualities.
Exactly. And Russell felt these impredicative definitions were trouble waiting to happen.
So can you give me a more concrete example of why he thought this was problematic?
He used this example of a typical Englishman, defined as someone who has all the properties that most Englishmen have. The problem, as he saw it, is that this definition of typical is referring to all properties, including typical itself.
Oh, I see. It's self-referential.
Exactly. It creates this possibility of a typical Englishman being, well, untypical, just by definition. It has that same kind of paradoxical flavor as the liar's paradox.
It does. So how did the ramified hierarchy address this concern?
The main idea was to categorize properties into different orders, like levels. So first-order properties, those are the ones that don't refer to all properties, just like your Napoleon was Corsican example. Then you've got second-order properties, and they can refer to first-order properties, but not to second-order properties themselves, and so on, up the ladder.
Creating a strict pecking order for properties.
Exactly. And if you're defining a property of certain order, you can only refer to properties that are lower down on the ladder.
To break those self-referential loops.
Precisely.
It's interesting that Poincaré was thinking along very similar lines at the same time. He emphasized predicative classifications, right?
He did. His big idea was that you should never define something in a class by quantifying over that very class in its definition.
Can you unpack that a bit?
Sure. He used the example of inductive properties and how we usually define number. The standard definition is impredicative, he argued.
In what way?
Well, we usually say a natural number is something that satisfies all inductive properties, right? But that's a problem, Poincaré said, because the property to be a natural number itself seems to be an inductive property. So you're using the thing you're defining in its own definition.
Ah, that circularity again.
Exactly. His solution, much like Russell's, was to create a ramified hierarchy. You'd start with first-order inductive properties and say numbers of order 1 are the things that satisfy those properties. Then you move up to second-order inductive properties, which can refer to the first-order ones, and you get numbers of order 2, and so on.
So a number of order 2 is automatically also a number of order 1.
You got it. It's like a nested structure.
I see. But our source points out that this ramified approach, while elegant, gets really complicated really fast.
It does. Even basic things become tricky, like if you've got two numbers, x and y, that are both in a certain order, say n, in the hierarchy, is their sum, x plus y, also in that same order?
Good question.
Well, it turns out that if x and y are of order n plus 1, their sum is only of order n.
Really? That doesn't seem very intuitive.
It's not.
Eh.
It makes even the simplest arithmetic operations way more complex than they need to be.
Right. And it gets even worse when you try to define things like natural numbers themselves as classes of classes, which was Russell's initial approach, following Frege. Within this ramified hierarchy, you end up with natural numbers of different orders, which makes even basic statements about them incredibly convoluted.
True. But even with these difficulties, people like Twistek and Skolem actually tried to develop arithmetic within this ramified framework.
Shows how appealing it was, at least initially, to try to address those philosophical worries about circularity.
It does.
What are some other examples of impredicative definitions that caused problems?
One classic example is the least upper bound of a bounded set of real numbers.
Huh.
If you define a real number as, say, the set of all rational numbers less than it, then the least upper bound of a set of real numbers is the union of all the sets in that set.
Okay, that makes sense.
But the issue is, this definition is talking about all the sets in that set, which could include the least upper bound itself, if it happens to be represented that way.
Oh,
So you're back to that self-referential issue.
right. And in the ramified hierarchy, wouldn't the least upper bound of a set of first-order real numbers end up being a second-order real number?
Most likely, yes.
It all gets very tangled. And, of course, Leibniz's definition of equality, as we talked about, is also impredicative.
It is. And Russell knew about all these complexities, of course. In the second edition of Principia Mathematica, he even thought that the hierarchy of natural numbers might collapse at some point, which would simplify things a lot.
That'd be nice.
It would. But later on, Gödel found a problem with Russell's reasoning about the collapse. And then Myhill came along and actually proved that the ramified hierarchy doesn't collapse at any finite level.
Oh, so no easy way out there.
Nope. And you run into a similar problem if you try to use Cantor's theorem within the ramified hierarchy.
So it seems like this hierarchy, while conceptually appealing, just creates too many problems in practice. Which brings us to that famous or maybe infamous addition to Principia Mathematica, the axiom of reducibility. This was controversial, wasn't it?
It was. The axiom of reducibility basically said that for every predicate, no matter what order it has in the hierarchy, there's an equivalent first-order predicate.
Equivalent, you mean?
I mean, they apply to the exact same thing. So for equality, for example, it meant assuming that AB is true if and only if A and B have all the same properties, regardless of the order of those properties.
Yeah.
And there's always some first-order relation that captures this equivalence.
So you're essentially collapsing the whole hierarchy down to the first level. I can see why that would be controversial.
Right. But without it, most of math would become insanely difficult, if not impossible. Imagine trying to prove things when basic concepts are scattered across different levels of this hierarchy. It would be a nightmare. And the funny thing is, even though it felt circular and went against the whole predicative idea, it didn't seem to cause any contradictions in the system.
Pragmatism winning over philosophical purity.
Something like that. But logicians like Trestek, and later the philosopher Frank Ramsey, they pointed out that this axiom kind of defeats the whole purpose of the ramified hierarchy in the first place. If every higher-order predicate has a first-order buddy, then why bother with the whole complicated hierarchy?
Right. It's like you're taking a shortcut that bypasses the whole structure you built.
Exactly. And this realization led to a shift in thinking. Logicians started to embrace impredicative definitions and work with a simpler extensional hierarchy. Individuals, sets of individuals, sets of individuals, and so on.
A more straightforward approach.
Exactly. And that's the kind of system you see in Gödel's work from 1931 and Church's work from 1940.
So simple type theory, despite those impredicative bits, really paved the way for modern approaches to logic and set theory.
It did.
But the axiom of reducibility, that remained a bit of a philosophical thorn in the side, didn't it?
It did. The great mathematician and philosopher Hermann Weyl, he called it a bold and almost fantastic axiom. He wasn't a fan. He criticized it for lacking any real justification.
And later work in proof theory showed that adding this axiom really boosts the logical power of a system.
It does.
But the ramified hierarchy, that wasn't completely forgotten, right?
You're right. People started to think about extending it into the transfinite.
Transfinite.
Yeah, like using those infinite ordinal numbers. Poincaré himself talked about a number being inductive of order, omega, if it satisfied all inductive properties of any finite order. And later, Gödel showed that you could actually prove a version of the reducibility axiom when you extend the hierarchy of predicates over the natural numbers into the transfinite, specifically at the level of omega 1, the smallest uncountable ordinal.
That's pretty mind-blowing.
It is, right. And that discovery linked the ramified hierarchy to Gödel's model of constructible sets in set theory.
Which is?
Well, in this model, all the subsets of the natural numbers have a size of omega 1 and reflects the structure of the ramified hierarchy up to that level.
Yeah.
And this connection actually provided a relative consistency proof for the continuum hypothesis, which was a big open problem in set theory for a long time.
Wow. So the ramified hierarchy, even though it was problematic in some ways, turned out to have these deep connections to other areas of math.
Exactly. And it also became a subject of study within proof theory.
Proof theory. Remind me what that's all about.
It's the study of proofs themselves as mathematical objects.
Right.
So after Gensen showed that you could prove the consistency of arithmetic using transfinite induction up to the ordinal ver epsilon, people started to ask, what about the ramified hierarchy? What are the ordinals associated with its different levels?
Good question.
Kurt Schutt worked on this, and he found that as you climb the levels of the ramified hierarchy, the ordinal strength of the system just explodes. Yeah. Like the first level corresponds to the ordinal ver epsilon, then the second level is ver epsilon, and so on. It gets really big, really fast. And Gödel also explored extensions beyond omega 1 and found that a form of reducibility is provable there too. Then you have more constructive approaches, where you build the hierarchy step by step up to and even beyond ver epsilon. And these have led to some really important ordinals like gamma, which is seen as a kind of boundary for predicative systems.
Okay, this is getting pretty deep into the weeds of proof theory, but I'm curious.